All right, in section 1.7, we're going to review some of our basic functional operations, and then we're going to learn some new functional operations as well. So if you have any two functions, we'll call them f and g, you can add, subtract, multiply, or divide those functions just using basic algebraic operations. Sometimes if you have rational expressions, you have to do things with fractions. If you have polynomials, you have to use the things like FOIL and combining like terms. So really what we have here is you can just see some of these review ones where we're doing addition where you add two functions, subtraction where you subtract two functions, multiply where you multiply two functions, and then divide where you're dividing two functions. The most important thing to remember when you're dividing two functions, though, the bottom cannot be 0 because you can never divide by 0. So just like we talked about the domain of a reciprocal function, can't be 0 on the bottom. Same thing with any division of two functions. So we have a couple examples here. We have f of x equals x plus 2, and g of x equals x squared plus 3x. And what we want to do is we're going to look how to find the sum, difference, product, quotient, and then we're also going to do negative 1/2 of g of x. So basically a scalar times a function. So if I look at the first one, which is f plus g of x, in this first one, I'm simply going to add the two functions together. So here's my f function, and here's my g function. So remember, when we add two functions together, we add two polynomials together, we just simply combine like terms. So the x squared doesn't combine with anything. The x and 3x make 4x, and then we have the 2. So just combining of like terms. Now the difference will be a little different. So if I look at the difference, I'm going to do f minus g of x. Looks very similar to above. We have x plus 2 minus x squared plus 3x. And you can see I'm always putting these in parentheses because that kind of helps in algebra to make sure we get the operations correct. Because when you have a minus sign, when you're subtracting, we're going to distribute that minus sign throughout the second parenthesis. So this will be x plus 2 plus negative x squared minus 3x. Because we're multiplying everything in that second polynomial by negative 1. Combining terms on that, we get negative x squared minus 2x, because we have positive 1x minus 3x, and then plus 2. For the product, when we're multiplying two functions, so we have f times g of x, same idea applies. We'll take the first one, x plus 2, and we'll multiply it by the second one, which is x squared plus 3x. Now in this case, when you have two polynomials multiplied in these parentheses, we're going to do the FOIL. So x times x is x cubed, x times 3x is 3x squared, 2 times x squared is 2x squared, and then 2 times 3x is 6x. Now the 2 in the middle will combine, so that's x cubed plus 5x squared plus 6x. So again, none of this is really new material, just kind of a review of algebra. Now for the quotient, we're going to do f divided by g of x. So that means we're going to take the top function, which is f, which is our x plus 2, and we're going to divide it by the x squared plus 3x. Now, there's not much I can do here. This is just the answer. But there are some domain restrictions we want to talk about, because if I simplify the bottom, you can see that this can become x and x plus 3. So there are two numbers x can't be. It can't be 0, because if I have a 0 for the first one, I'll have 0 times 3, which doesn't work. And it can't be negative 3, because if I put negative 3 in this parenthesis, it also won't work. So just remember, you can never have the denominator be 0. Okay, the last one we're going to do is negative 1/2 g of x. So this is just a number in front of a function. So it's going to be negative 1/2 times the g function, which is x squared plus 3x. And so all we're simply going to do is distribute here. So that's going to give me negative 1/2 x squared. And then 3 times 1/2 is going to give you minus 3 over 2x. So we're just distributing that constant to the function, and that's how you could do a scalar. All right, let's look at these other examples over here, where it talks about two new functions. We have f of x equals square root of x plus 2, and g of x equals x minus 3. So if we look at the sum of these two, f of f plus g of x, well, we're simply just going to kind of put them next to each other. So we have square root of x plus 2 plus x minus 3. Now, because the x plus 2 is in a square root, there's really nothing we can do to this. So this is just generally our answer. Now, there is a domain restriction because it has a square root. Remember, square roots have to be greater than or equal to 0. So the domain of this would be x greater than or equal to -2. Or -2 to infinity if we wanted to put it in our interval notation. Either way is fine. Now, as far as the difference, when you subtract, same kind of problem persists. We have f minus g of x. We're going to have the f function, which is square root of x plus 2, minus the g function, which is x minus 3. Now, the only thing I can really do to this one is distribute that negative sign. So I get square root of x plus 2 minus x plus 3. Again, same domain, x greater than or equal to -2. But not much else I can do. Now for the product, f times g of x, we're going to have a similar problem. We're going to have square root of x plus 2 times x minus 3. And unfortunately, unlike the last one when we were able to FOIL, one of these is under a root and one is not, so you cannot FOIL those together. Now, if they were both under roots or they both were not under roots, you can certainly multiply them. But with one of each, you cannot. And again, same domain restriction, x greater than or equal to -2, because it does contain that square root. So let's look at the quotient. Let's look at the division. So if I do f divided by g of x, we have square root of x plus 2 divided by x minus 3. Nothing very interesting about that, but the domain is actually very interesting because the square root says it has to be greater than or equal to -2, but then the denominator, x minus 3, x can't be equal to 3. So our domain ends up being all numbers greater than or equal to -2 except 3. So interval notation-wise, that'd be -2 to 3, parenthesis, union 3 to infinity. Finally, our 1/2 g of x, or -1/2 g of x, we're going to take -1/2 times the g function. So that's simply going to be -1/2 times x minus 3. I distribute that. So I'm going to get -1/2 x and then plus 3 over 2, or 1.5. Now this is just essentially a linear equation, so there are no domain restrictions for this. Every number is fine to plug into that. Okay, the last operation we're going to look at is a composition of functions, which is a new operation that you probably have not seen before. And that's when we're going to take a functional value of another function. So you can see the composition of two functions, f and g. It's written as f of g of x. So the little open circle represents of. So f of g of x is simply equal to f of g of x. So essentially what that means is if you have the g of x function, you are plugging it in to the f function. So everywhere there is an x, we are going to plug in the g function for that x. So we're going to take the functional value f of g of x. The one thing you have to also remember for composition of functions is they do have some domain restrictions. The two domain restrictions of f of g of x is all values that will make it undefined. So if it's a square root or a log or a reciprocal function. And also you have to look for anything that makes g of x undefined. So same thing, look for g of x. So you have to look for the final composition, and you have to look for g of x, which is the function you are plugging in. So let's look at a couple examples of finding f of g of x and stating its domain for a couple problems. So this first one, we have f of x equals x plus 2 and g of x equals x squared plus 3x. So we're going to find f of g of x. So that's f of g of x. So what we're going to do is we're going to take the g function, which in this case is x squared plus 3x, and we're going to plug it into the f function. Now, there's only one x in the f function, so I'm only going to replace the g of x in one spot. So the composition will end up looking like this. X squared plus 3x, that's where it was at first, and then plus 2. So this is our composition. So the f, what used to be x, the x gets replaced with x squared plus 3x, and then we just add the 2 on. So this is simply going to be x squared plus 3x plus 2. That is f composed with g of x. Now, domain-wise, I look at this final answer, which is just a polynomial. There's no problems there. There's no square roots. There's no reciprocal functions, no logs. So that's fine. Then I also look at the function I plugged in. I look at g of x. But g of x is also just x squared plus 3x. So there's no real problems there. So the domain is simply going to be all real numbers or negative infinity to infinity. All right, so let's look at another example. So this example, we have f is the square root of x plus 2, and g is x minus 3. So I'm going to try to find f of g of x again, which remember is f of g of x. So everywhere I see x in the f function, I'm going to substitute it with g. So there's one spot, so that will go in there. So we have square root. It used to be x, but now I'm going to replace the x with x minus 3 and then plus 2. So if I simplify under the root, I simply get x minus 1. So now we have to talk about the domain. So remember, square roots have to be positive or 0. So if I look at x minus 1 and set it greater than or equal to 0, that's going to give me x values that are greater than or equal to 1. So I know the composition's domain has at least numbers that are greater than or equal to 1. I also need to look at g of x, but g of x is simply x minus 3, no square root, no log, so it really doesn't add any restrictions to the domain. So the domain will simply be numbers greater than 1, so we'll say 1 with a bracket to infinity. So any value like that would be good for my composition. Let's look at one final example we have down here. And that is two rational expressions. Now these obviously have some domain restrictions because they have denominators. So we're going to find f of g of x. So we'll have to remember quite a bit of algebra to simplify these. So we're going to plug the g function. The g function in this case is 2 over x plus 2. And I'm going to plug it in for the 1x I see in the f function. So if I write that out, that's going to be 1 over, it used to be x, now it's going to be 2 over x plus 2 plus 2. So now we have to simplify this function, and this is what we refer to as a complex fraction. So the way we simplify this, we look at all the denominators in each term. So I see this has a denominator of x plus 2. This one technically has a denominator of 1 because it's just the number 2. And this is 1, so it technically has a denominator of 1. So I'll write what the least common denominator is, and the least common denominator in our case is going to be x plus 2. So I'm going to multiply all the tops by x plus 2. And what you'll see will happen if I do this, if I multiply this by x plus 2, and this by x plus 2, and this by x plus 2, it will cancel out this x plus 2. So what this ends up being is we have 1 times x plus 2. So x plus 2 on the top. On the bottom, we're going to get 2, because remember, the x plus 2 is canceled out, plus 2 times x plus 2. So now you don't see any fractions in the top and bottom, just a one denominator and numerator. So the top is x plus 2. The bottom is going to become 2 plus 2x plus 4, because I'm going to distribute that 2. And then x plus 2 over 6 plus 2x. So this is my composition f of g of x. So now we have to talk domain. So remember, we don't want the denominator to be 0 in our final answer, and there is a denominator. So we have to figure out what number makes 6 plus 2x equal to 0. So if I do a little algebra, that's 2x equals negative 6, that's x equal negative 3. So I can't have negative 3. But remember, I also have to check my g function. So g in this case was 2 over x plus 2. So that actually is a reciprocal function. So in this case, x can't be negative 2 as well, because negative 2 plus 2 equals 0. So you're always checking your final composition, but you also have to check your function that you plugged into the other, because if it's undefined, you can't plug an undefined value into another function. So the domain can't be negative 3 or negative 2. So interval notation for the domain would be negative infinity to negative 3. Union, negative 3, so double parenthesis to eliminate that value, to negative 2. Union, negative 2 to infinity. So remember, once you've watched this video, make sure you are reading the online textbook, taking notes on that, and then you can try the assignment that corresponds with section 7. Please let me know if you have any questions.